The tunneling phenomena is one of the striking features that distinguish the classical and quantum worlds. It becomes even more interesting when the barrier which a particle tunnels through is not constant but varies itself with time. Apart from a fundamental interest, studying this phenomenon might open a way to a range of novel applications from femtosecond nanoelectronics to scanning atomic microscopy with attosecond temporal resolution. In particular, tunneling in nanostructures and resulting charge transfer can be induced by an external pulsed laser field with controlled properties such as its duration, amplitude, and phase. Till now, theoretical analysis of the corresponding pulse-induced tunneling processes could be performed basically only numerically, apart from certain limit cases. In our paper, we developed a new general quasi-classical description that not only leads to analytical results, but also provide fruitful insights into the characteristics of the time-dependent tunneling phenomenon that remain hidden behind the calculation machinery of the numerical approaches. It is known for the continuous wave laser fields that the physical nature of the field-driven tunneling is governed by the so-called Keldysh parameter, which rises linearly with the field frequency but drops proportionally to the field strength. If it is small, an electron prefers to penetrate through the barrier at a time moment when the field acquires one of its peak values and needs then to overcome the whole corresponding barrier width at the given initial energy of the electron. If it is much larger than unity, the electron escapes from the barrier basically just absorbing photons from the field. The latter can be described by a standard theory of multi-photon transitions. In our study, we were interested in the intermediate regime, with the Keldysh parameter being on the order of unity or somewhat higher, where the electron gains energy during the tunneling event, termed non-adiabatic tunneling regime. Moreover, we generalized the corresponding consideration to the case of ultra-short duration, when the applied light pulses consist of just few numbers of oscillation cycles down to the subcycle regime. We theoretically investigate non-adiabatic tunneling in this regime based on the quasi-classical viewpoint. The quasi-classical approach provides an intuitive picture of the quantum reality by describing the quantum dynamics as the classical one, but extending it to the complex planes for time and space coordinates. For example, consider the particle with negative energy inside the tunneling barrier. Since the square of the velocity gives the kinetic energy, such negative energy can be naturally attributed to a velocity which is purely imaginary. Also, the time determining the process characteristics becomes imaginary. Technically, we base our theory on a so-called Lagrangian formulation of the quasi-classical imaginary time method, allowing then actually any complex values of time. By doing this, we do not need to rely on additional ad hoc assumptions and are able to find the spatio-temporal structure of the resulting quantum solution. The structure of our paper is the following. Firstly, we investigate the case when the tunneling between two metallic nanocontacts is driven by an ideal half-cycle pulse. We find two main solution branches, each time having the form of a quasi-classical wave packet of tunneling or evanescent electron density respectively. Observing the behavior of these two solution branches' independence on the inner contact distance and field strengths allows us to identify two physically different tunneling regimes and a crossover between them. Secondly, we consider realistic temporal profiles of few femtosecond pulses. We demonstrate that by manipulating the carrier envelope phase of these pulses, we can control the preferred direction of the electron transport through the nanogap. We also find analytic expressions for the tunneling probability, independence on the pulse parameters. Finally, we show that the times when the outgoing electron trajectories emerge from under the barrier can be temporally shifted with respect to the peak positions of the laser pulse they originate from.